Hi everyone, and welcome back to our 10th lecture on reinforcement learning. Today we're going to be talking a lot more about approximate dynamic programming and the algorithm that you've seen in the last few lectures, especially in model-free reinforcement learning in terms of this paradigm. So let's dig in. So last lectures, you've already seen MDPs, dynamic programming. We touched a bit about approximate dynamic programming, mostly as a framework to guide you through the model-free and model-free prediction and model-free control. We've also seen a bit far back Bellman equations and their corresponding operators. We're going to be reusing these concepts today, and we touched upon with Hado on reinforcement learning under function approximation. And we'll see a bit more of that in the next lectures with Matteo on particular deep reinforcement learning. Now, this lecture, we're going to be revisiting the approximate dynamic programming under these two sources of error: estimation, so not having access to the true model and being forced, in a sense, to sample from the model through experience, paired with function approximation, which means that we are not in a tabular setting anymore. We can't represent the value functions exactly for all states in action, but we would use a function approximator to do that. Okay. And as I already mentioned, in the next lectures, you're going to see more of these paradigms. And most of the state-of-the-art research kind of falls within this paradigm. And in particular, removing the perfect knowledge of the environment assumption and going more towards a popular version of function approximation, which is deep neural networks. Okay. A couple of preliminaries. This have been introduced before, but just to recap and be on the same side, we've introduced previously the Bellman optimality operator. This was derived from the Bellman optimality equation, and the definition is in equation 1 here. To note that this Bellman operator has a unique fixed point, which is exactly the value function that we are looking for. That's why iterating this operator will eventually get us to the optimal value function. This is under no approximation condition with perfect knowledge of the model. So this is just pure dynamic programming. Okay, and then we had the Bellman expectation operator, which has similar properties. It's a contraction. It has one unique fixed point, but the unique fixed point of this operator is the evaluation of the policy pi for which this operator is defined. Okay, good. And just another reminder, dynamic programming through the lens of these operators. The two popular algorithms there that we've seen are value iteration and policy iteration, and you've seen approximate versions of this. For instance, Q-learning being an approximate version of a value iteration. So both of these say value iteration is just applying multiple times the Bellman optimality operator, and again, under perfect conditions, no approximation, this is guaranteed to converge to the fixed point of this operator, T star, which is the optimal Bellman operator, which is the optimal value function. And policy iteration was this procedure of starting with a particular policy, doing policy evaluation, which can be done iteratively via the Bellman expectation operator, or can be done in any other way, especially if we can solve the true system of equations. And then on top of this evaluation, we're going to do an improvement step, usually a greedy improvement step. And we've seen in previous lectures that is guaranteed to give us a better policy than the one we've just evaluated. And we just iterated this process by improving greedily on this evaluation. And at least in finite cases, this will eventually, because we're improving the policy at the each point in time, this will eventually get us to the optimal policy. Good. Okay. So now approximate dynamic programming, as you've seen before, removes a couple of the assumption of the true of knowing the underlying MDP and being able to represent exactly the value function. So moving away from tabular and moving away from the assumption that we can actually evaluate perfectly the expectations needed in these updates. Okay, and by doing so, in one of the cases where we don't know the underlying MDP, we're going to be introducing some sampling or estimation error because we're trying to estimate an expectation via samples. And in the other case, we're going to be introducing some kind of approximation error because we might not be able to represent exactly in the parametric function class we've chosen the true value functions that we want to estimate at each point of this process. All of these procedures are kind of iterative procedures, so we'll have a lot of value functions in between value functions that we would need to estimate. So whenever neither of any of these functions cannot fully be approximated by the approximation by the parametric class we've chosen, then we incur some error at that iteration. So it's not only that the true solution can't be represented, it might be that the true solution is representable, but the intermediate steps, the intermediate value functions that we're trying to approximate are not representable under the parametric class, then we're still gonna incur some approximation error. Okay. And of course, as always, even under these conditions, the objective of RL is to come up with a policy that is hopefully close to optimal behavior. Good. So let's look more in depth at the approximate value function value iteration paradigm. So this is close to what you've seen, for instance, in Q-learning. So again, as a reminder, just this is value iteration through the lens of the Bellman optimality operator. So we start with the value, and at each iteration k, we update vk plus 1 towards, or in the exact case, with the one-step application of the Bellman optimality operator applied to the value function at the previous iteration. Okay, and iterating this as k tends to infinity, this the sequence of value function eventually converges under the infinity norm to v star. If this is still not clear to you, I would urge you to go back to our second lecture on dynamic programming and see the arguments there. Okay. Now, the approximate version of this is basically we're gonna do this iterative step at each iteration k approximately. So that's what this A stands for. And again, this approximation can be based on the function approximation or based on the fact that we actually don't have access to a t star, and we'll have to sample to approximate it. And the same as before, we're gonna do a greedy improvement step on whatever value function we approximated here. Okay. Now the question that arises, of course, is if we iterate this process, would we converge to the optimal value function? Will we converge at all? And in general, that's a no. It highly depends on what the approximation here is. Okay. The nice things that we kind of hinted last time is that even if we don't converge all the way to the optimal value function, we are actually interested only in the quality of the policy, this derived greedy policy with respect to the estimate at one point in this iteration. We're never going to do this iteration forever. And we're trying to understand how good that policy is. Okay. And just to be clear, usually we would be using something like the Q version of approximate value iteration, where we do exactly the same process, but not for V, but for Q. Again, start with an arbitrary value function Q0, update towards the one-step Bellman operator with respect to Qk at iteration k plus 1, and then return as a control policy the greedy with respect to that estimate. This is what we use usually in practice, especially if we don't have a model, because remember that to derive this greedy policy, we actually need the action value function to just basically pick the argmax of the Q value function. If we don't and we have only V, then we would have to have at least a one-step model in order to derive the greedy policy. So usually we're just gonna go for approximating the Q value. Okay, and as I hinted before, we really want to be able to say something about the quality of this greedy policy derived after n steps of iterating this approximate value iteration process. And this is what the following theorem is saying. This is an old result from '96, but still a very important result in the field that basically does this for us. So we're gonna bound under the infinity norm the performance of the policy at the nth iteration of this value iteration procedure with respect to the optimal value function. So that's what this first term says. And this is gonna be bounded by two factors. First, the initial error. This is basically defined in the second line here, is how far is my initialization with respect to the optimal value function with respect to the L infinity norm. So this is the second term in the bound. Okay, and the first term here is the approximation error that I'm gonna incur at iteration k. Okay, so usually at iteration k plus 1, I'm gonna try to estimate, I'm gonna try to back up t star q k, but because I'm in an approximate setting, what I'm actually gonna be my next q k plus 1 would actually be a t star qk. So this accounts for how much error am I incurring by introducing this a in my backups in the value iteration. Okay, so this should be kind of intuitive outside the the terms in front, that our performance of the policy after n iterations of this value. Iteration is bounded by both where we started, so our initial error, and the approximate error that we're going to be incurring at each iteration. Cool. So next we're going to move into the proof of this statement. Okay, let's start by first denoting the maximum error that we can incur up to iteration n. So for any iteration k in between that and n, we are maximizing over the approximation error. This is, again, usually for dynamic programming, this would be qk plus 1. But in approximate dynamic programming, we're introducing approximation, so this term will be our value function at iteration k plus 1. So discrepancy between this k plus 1 and this k plus 1 is what the approximation error introduces. Okay, so we're gonna now maximize over all of these errors and denote that by epsilon. Okay. Next, the first thing we're going to do is try to relate the value function at iteration k plus 1, and in particular at iteration n, with respect to the optimal value function. Note that this is not exactly what we want. The statement of the theorem is actually saying something stronger in terms of the performance of the policy derived based on the estimate at iteration n. So if we have qn, then this induces via greedy this policy qn is greedy with respect to the estimate that we had at iteration n, and we're interested really in the value of that policy. Okay, but we'll see that this is really simple based on the result that we've had in the last lecture on dynamic programming, where we have a result that relates the performance of greedy policy with respect to the value function that induces that policy. We're gonna just revise that result in the next slide. But first, let's look at this equation. Okay, and we're gonna break it down into a couple of terms. So first, we add and subtract the same term, and due to the triangle inequality, we can split these apart. This is an upper bound to the left hand side. Okay, and then note that this term is exactly the approximation error at iteration k, which is upper bounded by definition by this epsilon, which maximizes over all the iteration up to n. Okay, so that's why we get this term being less than equal than epsilon. And then on the first term there, we are using that the Bellman operator has a unique fixed point, which is q star. So just as a reminder, that means that this holds, again, because q star is the unique fixed point of this operator. And then we're going to be using the fact that this operator, q star, is a contraction. Actually, it's a gamma contraction. which means that less than equal than gamma. So so this term now is less than equal than this term. Okay, and now what we've actually achieved is a recurrence relationship between how far the value function at iteration k plus 1 is related to how far it was at the previous iteration qk. Okay, and what we're gonna do now is basically unfold that equation. So this is the equation that we're gonna, like, the inequality that we're gonna be using, and we're gonna apply it at previous iteration. So first for k, and we're gonna relate it to k minus 1, then k minus 1 to k minus 2, and so on and so forth. And what we get is we can relate this to the initial error at iteration k equals 0, and this term, which is the discounted errors. It's an upper bound actually of the discounted errors that we've encountered at each iteration. And this is, of course, also less than equal than if this would have been, k equals capital K actually goes to infinity. So this now is upper bounded by the mistake, or the how good our initialization was, and this term accounting for the errors that we've seen. It's actually an upper bound on the errors that we've seen throughout this approximation at every iteration k. Okay, now I'm just restating this here. Is the same equation as here. And now the last step is to relate. Apologies for the buzzer there. But as I was saying, we're gonna now relate this result to the performance of the policy induced by the estimate at iteration k or iteration n. So just as a reminder, the policy that we're deriving is greedy with respect to that estimate, and we are interested in evaluating that policy at iteration n. And for that, we're going to be using the result we had in our last lecture on dynamic programming, which was the performance of the greedy policy based on an arbitrary value function qk. And that, if you remember this, was the performance of the derived policy q pi k can be bounded in terms of the performance of how far this estimate on which we're basing the greedy on is with respect to the optimal value function. Okay, and note that we already have this term upper bounded here, and just by plugging in 10 into equation 11, you get exactly the statement of the theorem. Okay, now that we've proven the statement of the theorem, let's look at some of the implications that this has. And first, we're going to look at the last term there. So some of the implications are, as n tends to infinity, this term in red tends to 0 as this gamma to the n decays exponentially fast. So what that means is that although at each iteration n this term appears and is bounding our performance with respect to the initial point, our initialization of this process. As n tends to infinity, basically this term will disappear, which is good news, which means that in the limit we will have no dependence on the initialization point. Okay. Another question here, just as maybe as a sanity check, is what if we do initialize, by chance at exactly the optimal point at Q star? Well, let's say what the bound says. So obviously this the second term goes away because the norm there of the initial error is 0, but you can see that we are left with another term here, which is still the maximization of all the approximation error that we would encounter in each iteration. Okay. Now the question becomes, would that be 0 in general? Let's consider just one iteration of this process. So let's say we start at Q star as our first iteration of this process. So Q0 is Q star, and our first iteration of this approximate value iteration process gets us Q1, which is the approximate version of the one-step application of the Bellman operator to Q0. Because Q0 is Q star, then the application of the Bellman operator to Q star is Q star. So Q1 is actually the approximation operator applied to Q star. Now, in general, this might not be 0. So, for instance, if A is an approximate a hypothesis space, let's say, that is not within our class of approximations, then this error at the first iteration might not be 0. So even initializing at the right solution, in a sense, by approximation we might move away from this solution. That being said, if this initial point has to be in the function of approximations, then this has to be 0, because the projection here, just in terms of coming back into the class of functions, this would be like not lossy. So the projection of Q star under the function approximation would just give you back the Q star, because that's the closest point in the function approximation. Again, if A is something like an estimation error, where instead of having the true Bellman operator, we have a sampled version of this, again, this error at the first iteration might be non-zero, probably will be non-zero, which means that even if we initialize at the right solution, we might move away. And once we move away from the solution, we can further move away, and so on and so forth. So this result is very general, but it does state that even if we are close enough to the solution, it highly depends on what the approximation errors incur that each iteration will do, and how much we could in principle lose based on that. Okay. Now let's focus a bit on the other term, we've seen already that as n tends to infinity, the second term goes to 0, which means we wash out the initial approximation error. Now let's consider a hypothesis space, F. So this is where, let's say, our approximation comes from. And let's now have A be exactly the projection with respect to the L infinity norm. Okay, so this is the definition of this projection is now in the equation below. So we're just looking for the projection of G, a function or vector, under the L infinity, is trying to find in the space of value function F the closest point to G under the L infinity norm. Okay. Now, if we do that, then the approximate value iteration algorithm at each iteration k plus 1 will take the form of applying the Bellman operator to optimality operator to the previous value function, and then projecting it via this operator. Now, the thing to note here is that this combined operator, the approximation, just via the projection, we're still doing full dynamic programming in terms of using the expectation, using the true model here. So this combined operator is indeed a contraction operator in L infinity, because basically T star is a contraction with respect to L infinity, and the projection with respect to that norm is a non-expansional mapping. So the full thing is a contraction with the same gamma parameter. Because this whole operator is a contraction, this algorithm does converge. It is guaranteed to converge to a fixed point. Actually, because it's a contraction from previous Banach fixed point theorem, it has one unique fixed point. It says a fixed point, and this is unique. That has this equation. And as before, if Q star, the thing that we're looking, is indeed in F, is under our functional class, then the above algorithm, this iteration in red, actually converges to the true value function. And this is easy to see if we again remember that this algorithm has one unique fixed point, and you can plug in this equation if F equals the projection via the L infinity norm T star F, and see that Q star actually satisfies this equation. Cool. So now we've got, at least on the function approximator, still full model of the MDP, a converging algorithm that, at least if the true value function, the one that we're looking for, the optimal value function, is representable in our functional class, then we are guaranteed to converge there. Even if it's not in if Q star is not in that functional class, this algorithm still converges. It just might not be to Q star, because as we've established, Q star is not representable in F, so we can't hope to recover something. We can't recover Q star via this parameterization. Okay. Let's look now at some concrete instances of this paradigm. And although I've just proposed a convergent algorithm, we'll see that this algorithm is somewhat impractical, and we're gonna try to fix that. And we'll see that trying to fix that actually gives us some of the popular algorithms that you've seen before and that are now used in the literature. Okay, so let's first have a clear instantiation of the algorithm that we've just proposed. So at each iteration k, we're trying to approximate the one-step Bellman operator by projecting back with respect to the L infinity norm under some hypothesis class F. Now, for concreteness, we're gonna consider F to be the space of all linear functions with respect to some feature space phi. So all of the functions, all of the qk in all of these iterations will have to be represented or approximated in this functional class. Okay, and then doing that, we obtain this simplified algorithm. At iteration k+1, we're looking in the space of linear value functions of the point that best approximates under the L infinity norm T star qk. And because we have only one set of parameters, which is w, the weights of this feature vector, the equation 12 can be reinterpreted as just finding at each iteration k or k+1 a weight vector k+1 that minimizes this equation. Now, how would you solve this equation? How tractable is this, even under a very one of the simplest hypothesis classes out there? Now, here are a couple of potential problems, but before I flash that, just try to take a moment here and try to think how you would find this vector wk+1 at each iteration, and how hard or how easy would that update look like, or what's the complexity of that update. How would you do it for a linear class, or something like a neural network, or any kind of other function approximator class there? Okay, hopefully you've at least tried this mental exercise and see that this is not trivial. And there are basically two problems there. One is that the L infinity minimization is typically hard to be carried out. Usually we are using different norms, more prominently something like L2 that is very well behaved and easy to optimize. In the linear case, this has a closed form solution. L infinity is usually a much harder optimization problem, and as you've seen in the previous lectures, and this is the general assumption, I guess, in reinforcement learning, is that T star is typically unknown and has to be approximated somehow, usually from samples. So here are some proposals of easing these problems. So first, I just hinted at this, that instead of L infinity, we're just going to replace that with something like L2 that is much easier to optimize. So instead of having now the L infinity optimization there, we're gonna do the same thing, but find the point in f that is closest to t star q k with respect to an L2 norm, or an L2 norm with respect to some probability distribution mu. Okay. And hopefully you know how to solve this. Any kind of like squared regression kind of thing will tackle that. So in most cases, this will have both at least for the linear case, a fixed like tractable form, and if not, in most of the other cases, we can do something like backprop and just take gradients with respect to this loss. And you've already seen, in the lectures in model-free control and variants of that, in order to approximate T star, we're just going to sample. And usually we have this tuples of S, A, R next state that we're going to sample with respect to this distribution, with respect to that norm, and our transition model. And we're going to approximate this term T star Q QK by this YT target for each sample. And this is just, again, the true operator, the true T star would be just an expectation of YT for all the samples, ST, AT, RT plus 1, ST plus 1. Okay, so now what we get is that at each iteration, we're going to find in our hypothesis space F, Q, W. These are the parameters of our function approximator. We're still using a linear function class that minimizes the square loss. And this is now a sample square loss rather than the true expectation loss. Okay. So this is just restating what the last equation was, and just reinterpreting YT as an approximate application of the Bellman optimality operator to the previous value function at iteration k. And this actually is a very general recipe for coming up with fitted Q iteration kind of algorithms, or just simple Q-based, Q-learning based algorithms. And there are a couple of dimensions there that we can vary. One I've really never used, that we're using here, linear parameterization. So this can be done with any kind of functional class F that can be parameterized by, as we did here with linear function classes, with neural networks, kernels, whatever your parameterization of your regressor is, anything can go in there. So these are the the parametric class that we're gonna be approximating the intermediate value functions with. Now there's a couple of other dimensions that we can vary. The other one is, again, we're gonna be approximating T star, the application of this operator. And in order to do that, we're gonna have to sample somehow. And this can be done online, can be done from a fixed, predefined, or a given kind of data set. Someone, gets you some data, some previous intervention protocols, some previous behaviors of policies that have been used in regulating a power plant or something like that, and those are like, just a fixed data set. You can also have a replay kind of model, or a replay memory, or a generative model where you can sample from this model to generate those samples. So all of these are, a way of approximating that operator via samples. But how you generate the samples and where they come from, it's it's a free dimension in a sense. And the last dimension there that is free also has to do with how we approximate this one-step Bellman operator. And the simplest one is the one we've used before. This is basically Q-learning. The other instantiation, the second instantiation there, is instead of this the application to the previous estimate, we have something like a target network that we keep fixed. It's almost like saying we at one point decide that iteration k is the target network that we saved, and we're gonna keep that for a while and make estimates and updates. And when we change the target network again, we're gonna call that iteration k+1. And there are multiple other versions of this target that can be done via off-policy learning and multi-step operators, where we can get not a one-step estimate of this operator, but maybe multiple steps estimate to speed up the credit assignment. And you're gonna see that in the next lecture with Hado, both of these variants. But again, this is a very general recipe, and there are, as I said, like these three dimensions you can pretty much mix and match. So let's look at one particular instantiation of this recipe, which is DQN. I'm sure you've seen this before, or at least you've looked at the paper. And the DQN is one of these algorithms that does follow this recipe. And in particular, for the approximation class, we chose neural networks. The samples are sampled from a replay, and the target here in the regression is based on a target network. Okay. Now, here's another instantiation of this, which is batch RL, where we can't interact necessarily with the environment. Is the examples I mentioned before, that maybe someone hands you in some data that has been collected under some policies or under human interventions or any kind of other data set, and you wanna still make use of that. So the function approximator there can be whatever is appropriate for the size of data or the problem specification, the observation set. And then we are working with the fixed data set, and let's say a option here for instantiation is just the one-step approximation of the Bellman operator via one sample, which is what the first line here says. This is probably the first thing that I would try. But of course, like you can have something like just more generally off-policy updates. Because the data set is fixed and you didn't have necessarily access to the policy that generated that data set, this might be hard. So Q-learning, so the first version there, this one, is probably the easiest. If you do have access basically to the collection policy, then you can do something more fancy in terms of off-policy updates. But again, in both of these examples, I'm kind of assuming that the data set that you are given is not the current policy that you're trying to evaluate. So this will be off policy most of the time, if not all of the time. I mean, for the control problem, we will always be off policy because the data set was collected under a particular policy, versus now at each iteration we're changing the policy. Okay, and another example here is what you've seen in the last lecture, which is something like Dyna. Again, we can choose whatever approximation family we choose to, and this is okay, this is a mistake. It should be samples are both online and from a replay model, and the simplest instantiation of Dyna will choose to do something like Q-learning, which is the one sample instantiation of this operator. Okay, that's it for approximate value iteration. Next, we're going to be looking at approximate policy iteration, the other algorithm for doing control. This is a much less studied, I guess, or less popular paradigm, but it's good to go through it because there are many algorithms these days that do follow that. But most of the algorithms that you will encounter in control, especially for off policy, actually follow this kind of recipe of fitted Q iteration with one of these dimensions varying, or an instantiation of one of these dimensions. Cool. We start with a reminder of the policy iteration paradigm. This again is the iterative procedure where we start with the policy at the initialization, and we iterate this process of policy evaluation and policy improvement, in our case greedy improvement. So at each point in time we're evaluating the policy derived at the previous step, and we make a greedification step with respect to that. And we know that at least in finite cases this will converge to the optimal policy. Now, the approximate setting, actually the approximation occurs in this policy evaluation step only. And now the value we derive at, or our approximation at iteration I, is the one that would provide the argument for the greedification. So instead of doing a greedification with respect to the actual evaluation of our previous policy, we're going to do a greedification with respect to the approximation to that evaluation problem. As hinted before, this usually does not converge to the optimal value function, but nevertheless, what we're really interested in is the quality of the policy that we're going to get after, let's say, iteration k. In this particular notation, iteration I. So in general, we're interested in the quality of the policy pi I as determined by q pi I with respect to, let's say, the optimal value function. So how good is that policy after I iterations of this procedure? And this is exactly what the next result we're gonna look at quantifies. So considering an MDP and QK and pi k are the value function at iteration k, and the greedification at iteration k minus 1, then we have the following statement. So we can bound the quality of the policy at time at iteration k by the approximations errors that we've incurred up to that point. Actually, it's a much stronger statement than this. Is saying the in the limit, the lim sup of this error, so your error with respect to the value function, is upper bounded by the last errors, like the convergence of this approximation errors as you approach convergence. Okay. We're gonna try to prove this, but first some notation. I think first of all, this should be a somewhat intuitive statement. The same as before, the quality of the policy that you are gonna get after k iteration is bounded by the errors we're making in this approximation, but this is actually a stronger result, as I said, as these things, the approximation errors, might still converge in the limit, or at least they are bounded, which means that this this term is also bounded and will converge at least within that bound. So it might oscillate around a fixed point, but it is bounded by the by how much the approximation errors vary in the limit. Okay. So a bit of notation before we jump into the proof. You've seen these notations before, just as a reminder. So we're gonna denote via P the matrix corresponding to the transition kernel, and this is the entries of these P are SA and S prime, which the entry SA S prime denotes the probability of transitioning to S prime, considering we started in S and took action A. This is just the transition kernel. And then P pi is the transition probability corresponding to policy pi. This is a number of actions, a number of states by number of actions, number of states. So this is basically a probability transition between SA and SA A prime under policy pi. Okay. And just a reminder, under this notation, the Bellman equation can be written in matrix form, as we've seen before in policy evaluation. Okay. So having this in mind, let's start the proof. First thing we're gonna do is look at this quantity that we call gain, which is the performance of policy at iteration k+1 versus the policy at iteration k. So between two consecutive iterations of approximate policy iteration, where we have two policies at these iterations, and we're saying like how much better is policy at k+1 with respect to the policy at iteration k. Okay, and first we're gonna try to say something about this quantity, and then we're gonna relate this quantity with the thing that we're actually interested in, which is the performance with respect to the optimal policy. Okay. So the gain as defined here is just the difference between these consecutive evaluation of two consecutive iterations of policy approximate policy iteration, and this is just rewriting the above equation, just using that the fixed point of operators pi k and pi k plus 1 are the value function corresponding to these evaluations. Okay, and then we're gonna do we're gonna add and subtract a couple of terms there. Okay, this might sound a bit or might look a bit scary at this point, but it's just adding up subtraction, and it does have a it does make sense in terms of we always do this kind of procedure, just varying one term at a time. So if you look at the first equation here, 17, we are keeping the operator fixed, but we're varying the argument. In the next equation, again, we're keeping the operator fixed, but we're changing the argument. Now, in the next equation, we are changing the operator, but keeping the argument fixed. And in the last one, we're keeping the operator fixed between these two and changing the argument. So usually that's the kind of relationships that we're gonna have, because we're gonna exploit the properties of these operators. Okay, so I've just written exactly what we had in the previous slide, and we're gonna unpack these terms. Okay, let's look at the first term here. This is gonna be R. We're just unpacking the definition of these Bellman operators. Plus gamma. And sorry. K plus 1 minus R plus gamma by plus 1 at, okay, and we can see that the R there goes away, and what we're left with is gamma pi k plus 1, and the difference between these policies, and this is what we called gain. Okay, and similarly we can do the same trick for this this equation, and this would be now the R's again simplify, and we have pi k plus 1 and the difference between this, which we called EK, which is the approximation error at iteration k. We're gonna skip this next term because this one has a very similar expression as the ones which we've just seen, because the operator is the same. Again, things simplify and we get the gamma p pi k and difference between these two. And again, these are, as before in the notation, it's minus the approximation error that we've incurred at iteration k. Just a bit of notation. EK, we've denoted this the difference between the evaluation of the policy pi k and the estimate qk, but not the norm of that. This has a sign, kind of thing. Okay. The last term that we have here is this one, and this one we're actually not gonna do anything but say that this is greater or equal than 0, and this is because this policy pi k plus 1 is the greedy with respect to this qk, which means that the evaluation operator there is actually the optimality, the one application of the Bellman optimality operator, and this is less greater than equal than any application of any other policy. Okay, hopefully you were able to follow that. If not, just stop the video and go over it. But these are exactly the same equations, but repeated in the slide. Okay, and again, this this particular inequality, you can unpack it explicitly if you want to convince yourself of that. But the argument we've just done is sufficient. Okay, so the only thing that we're gonna do now is basically upper bound this by this. So because we're gonna replace this term with 0, this is an upper bound, and we're just gonna plug in the terms that the simplification of the terms that we just had here. Okay, this is just rewriting. Okay, and rewriting a bit by noticing that the gain k appears both on the right hand side and the left hand side, and collecting those terms, we reach this final expression bounding the gain at iteration k. Okay, so this is the statement that we've just proven. Let's see a couple of implications. So this gain is really how much your policy, the quality of the policy that you derive, has improved from one iteration to the other. So the first thing to notice is that if EK, which is the approximation error, is by definition here is the gap between the actual evaluation of policy pi k and our approximation of that. So if that is 0, which means you have perfect evaluation at policy k, that thing is 0. So what we're getting is that the gain at iteration k is greater or equal than 0, which means that the quality of the policy at iteration k plus 1 is greater or equal than the quality of the policy at iteration k, which is exactly what we've proven before in terms of the greedy improvement step being an actual improvement step, a guaranteed improvement step over the whole state space. Now, if this term is different than 0, either larger or smaller than 0, this is a vector, so some of the entries might be positive, some of them might be negative, depending on your approximation. So can this gain be zero or negative, which would mean that at least in some states, the policy at iteration k plus 1 actually is worse than the policy at iteration k. So fortunately, under approximation, that can happen. And this is a very simple example just to give you an intuition where things can go wrong. So this is a simple MDP, 3 states. We have +1 rewards every time we transition at the end of this chain. The action space is left and right, fully deterministic. And we're, let's say at iteration k, the policy that we're evaluating is always going right. Okay, so if we evaluate this policy, the value function q pi k associated with that is as follows. So you can convince yourself that at least in the terminal states, if we're in state S1, S2, and taking action 1, which is exiting to this +1 reward, then we get the reward +1. If not, if you're in a state S0 and you're taking action 1, which is going to S2, you basically have a 0 reward plus gamma is 0.9 here. So 0 plus 0.9 and the value at this state, which is 0.9. The same for S1. We're taking one step with reward 0, but then we're discounting by 0.9 this already discounted value of 0.9. Now for action 2, this is a bit more complicated. We start with S1. So if you're in S1 and take action A2, you're going to transition to this terminal state and get reward 1. Now, if you are in state S0 and take action A2, you're going to transition to S1, and then you're still going to follow, this is evaluating this deterministic policy of always going right. So we make one transition according to A2, we transition to S1, and then from S1 we continue according to policy pi k. And according to policy pi k, we're just gonna go right, which means that we're making a step. We transition to S1, and then basically we're just discounting this value. Again, because in S1 we're not actually transitioning to the end state there. We're not actually exiting because we are executing a policy that will get us in the opposite direction. Okay, hopefully that's clear. Now consider, instead of having this full evaluation of policy pi k, consider an approximation. For different reasons, you might have either a functional class or based on samples, you get this approximation. And I've just made up some values that are, fairly close to what the evaluation would be, and it also maintains the the relationship between the action values, at least within the same action. Okay, so it's a reasonable approximation. Now, if you take the greedy with respect to this approximation to this evaluation, then you get policy pi k plus 1, which is this. So this is just reading out from our approximation. What am I going to do in S1? Well, I look at the value of these two actions. Obviously, A2 is better. I'm going to take that one. The same in S0. I look at the values of these actions. The one corresponding to A1 is better, so I'm going to take that one. And in S2, I'm looking again at the approximate values here, and I see that A2 in this case is better than A1. So the induced policy is the one depicted here. Okay, so let's now see this new policy at iteration k plus 1. If I were to actually evaluate how good that policy is, what would that evaluation be? And this is the evaluation for the policy that we've just computed, as greedy with respect to the approximation that we had. And this one, because of the cycle there, going back and forth between those states, actually has this value function, which you can see that if you compare the value of a policy at policy by k and the one at policy at k plus 1, you can see that even state by state, these things are either equal, or the policy at iteration k plus 1 is actually worse in this state, in this state, in this state. So actually, this is an extreme example of what I wanted to illustrate in the gain being negative, that in all of the states and actions, the gain is either 0 or negative. In most situations, you would have a mix of these, where in some cases it will be an improvement, but in some states and actions it can actually be negative. So it's not under approximation, it's not necessarily a strict improvement over the policy we had at the previous iteration. And there is where the problems with with convergence and with the monotonic improvement of these policies occurs. Okay. This was a bit of a detour, but I think it's good to have an intuition of what happens from one iteration to the other, and why this fails under potentially fails under approximation. So let's go back to the proof and actually go for the term that we are actually interested in bounding, which is the quality of the policy after k iteration with respect to the optimal value function. Okay. We're gonna denote by LK exactly the difference between the optimal value function and the quality of the policy at iteration k. Note that this thing is always positive, because by definition the value of the optimal policy is greater than the value of any other policy, and this is not an approximation. This is an actual evaluation of the policy at iteration k. Okay, so we're gonna start with just the definition. We're gonna do a similar thing that we did before, introducing the Bellman operators and using the fact that both of these value functions are fixed points of the expectation operator of pi k plus 1 and the fixed point of the evaluation, the expectation evaluator with respect to the optimal policy. Okay, and then we're gonna do exactly what we did before, which is introduce a couple of terms. So adding and subtracting a few of these terms. So just convince yourself that this thing and this thing goes simplify the same, this one and this one, this one and this one, this one and this one, and again the same recipe as before. We're just changing one thing at a time. So the operator state is the same, the argument is different. Again, the operator stayed the same, argument is different. The operator changes here, and so on and so forth. Okay, and we're gonna do a very similar thing that we did before, and basically bound all the terms that we've all these differences we're gonna either spell them out or bound them, in this case, by 0. Okay. The argument goes exactly as we did before. They are just rewriting what these differences are. Okay. So by collecting the terms here, and again this this particular inequality is follows the same argument as we had before, because this operator is the greedy with respect to qk. So pi k plus 1 is by definition the greedy with respect to the approximation qk. So that means this operator is actually the one-step optimality operator applied to qk. Okay, so this one is always better, or it's always greater than any kind of policy there. So any other evaluation operator applied to qk can't be better. Okay, so we're just gonna rewrite all of the terms that we and group all of the terms that we had here, and we're gonna now expand. We had a term here in terms of the gain at iteration k, and we've previously upper bounded this by this expression. So from 27 to 28, we're just plugging in the bound that we've previously proven for gk, and we're just bringing the terms together and rewriting a couple of stuff, and a couple of things simplify from 29 to 30. Okay, and now, sorry, as k tends to infinity, then we can introduce the lim sup of this quantity. So we have lk and lk plus 1 in one side of the equation and the other side of the equation in asymptotic regime. As k tends to infinity, this will become just this term, and then basically by rewriting we have this expression. So this term, all of this term here appears in the lim sup here. And the last thing that we're gonna do is we're gonna take the L infinity norm with respect to this equation. This is just rewriting what was on the other slide. Okay, and when we take that, we have a couple of terms there that will simplify. So in particular, if you look at this term, this fairly ugly term in equation 37, this actually simplifies to being upper bounded by 1 plus gamma over 1 minus gamma plus 1. This is using the fact that all of these matrices, pi for pi equals pi k plus 1 or pi k, or the optimal policy, all of them are stochastic matrices where the L infinity norm of all of these is 1. Okay, and that is it for the proof. If you rewrite basically this this term, you get exactly what the statement of the theorem says. So this is ek was exactly the the approximation error that we incur at iteration k, and this term just simplifies to this. Okay. Last thing we're going to do here is look at the concrete instance of this algorithm. And we're going to actually look at an algorithm that you've seen before, namely TD lambda with under linear approximation. Important to note at this point that this algorithm, at least in the form that I describe it here, will just implement the policy evaluation step in an approximate policy iteration loop. So it's just one of the steps that you have to do at each iteration k in this approximate policy iteration. It's the policy evaluation. This is mainly to show how one could reason under function approximator about the errors you incur at this evaluation step, because we've seen from the previous result that the quality, at least in the limit of the policy that you're gonna get at iteration k as k tends to infinity, as compared to the optimal value function, is bounded by how the errors at each iteration as k goes to infinity behave. So keeping those errors as small as possible in the policy evaluation case will mean that bound is tighter and tighter, which means that with respect to the optimal value function, you're losing less and less. So in the best case scenario, if those errors are 0, then you will converge to the optimal value function. So this is just an attempt at saying, under the normal scenario where we're using function approximator and we're using something like TD learning, how can we reason about the errors that we incur in this procedure? Okay, so we start with the linear functional space, and remember that the TD error under this approximation is defined as in equation 37, and then the parameter update W at each step after each TD error is updated with the magnitude of the TD error in the direction of phi STAT. Previously, I think you've seen this update for just the value function, not the state action value function, and this phi would be just a function of the state, and I think you've denoted it as xt. Okay. Well, under this paradigm, this algorithm actually has nice properties. So under the normal conditions of the learning rate here, satisfying these conditions, the sum of them being infinite and the square of them being finite, then this procedure converges to its limit, denoted here by W star, which is not approximating the optimal value function. It's just a notation for the fixed point. And all of this procedure is trying to approximate the value of some policy pi, the one we're computing the TD errors with respect to. And furthermore, it has been shown in the same paper of Tsitsiklis and Van Roy that the approximation error that we're going to be incurring by using TD in this in this formulation is bounded by 1 minus gamma lambda over 1 minus gamma, and this term is basically the best that you can do in this functional space with respect to this norm. So this is the point in F that is the closest to the value function you're trying to approximate, the closest to the approximation. So this is really saying that if I were to know this evaluation in advance, then if I were to just represent it in this functional space F, this is the closest that I can get in terms of approximation. And the whole expression is just saying that if I am doing this temporal difference learning under mild conditions, I'm going to be bounded by basically the best way of representing the value function that I'm interested in. This might not be exactly this point, the best approximator to Q pi, but it's very close to it. Okay. Just a couple of breaking down the statement as we usually do. One is you can lambda is a parameter in TD lambda, so one thing that we can ask is for which lambda is this upper bound the tightest, which means that we are guaranteed to lose the least. And it turns out, if you're eyeballing that or maximizing over that, is that for lambda equals 1, which corresponds to the Monte Carlo estimate, this bound is tighter. And I'll let you reason why that would be the case. Okay. The other question that might come to mind is, what if the value that we're trying to evaluate, the value of the policy that we're trying to evaluate, this Q pi, is actually representable in our space of hypothesis class? Well, then this part of the equation actually is 0, which means that Q W star, which is the point of convergence of the previous algorithm, is actually Q pi. So this is nice because we're saying that if my the function that I'm trying to represent is part of my my functional class, then I'm guaranteed with this algorithm to converge to that. Okay, now the question becomes, if this is not the case, if Q pi is not representable in our hypothesis space, then in general, well, we won't recover Q pi, but more general than that, the fixed point we converge to, this Q W star, is generally not the best approximation that we can get in this functional class, which is exactly what this term says. Okay, that is it for today. I'm gonna just do a quick summary now of the two paradigms in approximate dynamic programming that we've seen today. First, let's start with approximate value iteration. So we've proven this result, where, as a reminder, pi n is the policy that we're getting at iteration n of this procedure. Now, some lessons that we've learned. In general, the convergence is not guaranteed, depends highly on the approximation. But in practice, a lot of the algorithm that we've seen and we use in practice look at all of the instantiations that we had at the end of this section, seems to point that in practice this is generally well behaved. How do we control how good the policy that we're getting is? Well, the way to control this is to control the approximation error, and there are two sources of error: the estimation via sampling, so we don't have access to the true Bellman operator, and then there's the approximation coming from the functional class that we are using. We saw that although all of these results are in terms of the L infinity norm, and if we were to optimize with respect to that, we would get a safe algorithm in the sense of this being a full contraction operator and having a unique fixed point. For more efficient optimization, we usually substitute this L infinity norm with something like an L2 with respect to some distribution. Usually that will be the stationary distribution with respect to the policy that we're following. Okay. Note that the convergence point is not always Q star, especially if Q star is not representable in the function class. Even if that is the case, if Q star is representable in the function class, that is not enough. Just remind yourself of the example that we had, where really the insight there is that all of the intermediate errors kind of have to be zero in order for that to happen. It's not exactly necessary. It's the better way of saying it is that there might be errors at different points in that iteration process that can introduce errors that cannot be washed away, or at least we can't say anything, because this is kind of the worst case scenario. We're maximizing over all these errors. It might still be possible to converge to Q star. It's just at least based on this bound, we're not guaranteed to do that if we are incurring any kind of error at any of the intermediate iterations. Okay, and then what we've just seen is approximate policy iteration, and we've proven this result. A couple of lessons again. In general, convergence is not guaranteed, but again, in practice, this seems to be well behaved. Its popularity is not as great as the other paradigm, just because it does have this inner loop, this procedure of policy evaluation, which in itself is a problem of its own. You've seen the I guess the first lecture on model 3 prediction, that alone can be an iterative procedure itself. So it's not easy to evaluate a policy. So this being just a side inside step of another iterative procedure means that in practice it's not used as often. Okay. Again, the statement really, the only thing that says is that if we can control these errors, EK, actually the L infinity norm of these errors, then we are able to control the quality of the end result. And the same as before, there are two sources of error: sampling and functional class approximation. For We haven't gone really that much into this example, but for efficient optimization, again, we do the same thing of trading in the L infinity norm to a much more well-behaved approximation optimization problem in the L2 norm, and this is usually now with respect to the stationary distribution of the policy that we're trying to evaluate right now. A different way of saying this is that we are safe on policy. This is just the distribution of states that acting in the environment with respect to the policy that we're trying to evaluate, pi I in this case, will induce. Okay, and again, depending on the function class and a couple of mild conditions, we can obtain convergence, but the convergence point is not always Q star or even Q pi in the policy evaluation case. And moreover, we haven't touched upon this, but it is known that the convergent point for approximate policy iteration may not be unique, in the sense of this expression actually can have the behavior of stabilizing, like going down in terms of the error, and stabilizing around the band, around the point. It's still bounded by this term, but it might oscillate back and forth around that point. Okay. That is it for today. Any questions that you might have, please post on Moodle or come to the Q&A session. Thank you for your time.